So, determine the bending moment diagram of the continuous beam subject to the external loads shown below using moment distribution method. So, before we can draw the bending moment diagram at the end, we're going to fill out this table because it has all these steps that we need in order to do so. Now, you can see we've split it into sections. So, looking at the beam, we're going to have at point A a moment acting here called A moment AB, a moment acting here called moment BA, an equal and opposite one BC, and one here CB. You can see where we got all of these from. Now, here we have nodal moments at B, and at A and C we have end-member moments. So, to fill out this table, first we fill out the distribution factors. These basically distribute the nodal moments at B into BA and BC, but right now we can tell it's going to be 1/2 because it's just in half, like a symmetrical shape, although this is not always the case. So let's fill this in. 1/2. Now we want to find the initial moments. But before we find the initial moments, we're going to have to assume that node B is clamped. This is the difference. We basically have split it into two fixed supports. This means there's no rotations allowed. So, what we're trying to find is the internal end-member moments. So we know that moment AB is equal and opposite to moment BA. Moment AB equal and opposite to moment BA, but since they're equal and opposite, one of them has to be negative. Let's say this one. Same with BC. Moment BC and moment CB. Moment CB are equal and opposite. Now, which one shall we say is the negative one? Look at node B. The two moments acting at that point are MBA and MBC. And since MBA is the positive one, MBC, let's say this was the negative one. So, now we can find the value of the moment. Here, because we have a uniformly distributed load and two fixed supports, we're going to use this formula. So 10 times 5 squared over 12, 8 kilonewton meters. And here, because we have a point load and two fixed supports, we use this formula. And we get this. Now let's put this in our table. We want moment AB to put it here. We know minus moment AB is positive this. So positive moment AB is negative this. So minus 20.83. Minus 20.83. We know MAB is equal and opposite to MBA. So the value here is going to be 20.83. Let's check. MBA 20.83. MBA 20.83. Now, MBC, we want MBC. MBC is going to be negative 12.5. Negative 12.5. And MBC is equal and opposite to MCB. So MCB is 12.5. Let's check. Yes. Okay. Now, next step in our table is balance. This means we enforce moment equilibrium at B. So basically, you add up the moment you got here. So let's zoom in. We're going to do 20.83 plus, we keep the sign in the bracket, and this is the moment that we get at node B. But we want to apply equal and opposite moment to the residual balance at B. So if this one's acting in this direction, say, we're going to want to apply the same thing acting in the opposite direction to balance it out. So we're going to get the negative version of this, minus 0.833 kilonewton meters. But we can't write this in our table just yet for balance, because the moment above is distributed to the two ends by the distribution factors. So this moment that acts at B is distributed due to these two factors. So we have to half the value of minus 8.33 by 2. So minus 4.165. So on each side we get minus 4.165. This is how our moment distribution factors have split up the moment at B. Now, carryover. What does this mean? The moment acting at BA, let me use this, at BA, so here, half of it is going to be carried over to moment AB, because we have a fixed support. If this was a pin end, the carryover moment would have been 0. But for fixed support, the moment carried over from the nodal moment to the end member moment is half. And same sort of story goes for this one. So half of the moment here from BA is carried over to AB, and half of the moment from BC is carried over to moment CB, because they are fixed ends. Once again, if they were pinned ends, the moment carried over would have been 0. Okay, so half carried over, we're going to have a value of minus 2.083 on both sides. Now, final step, summation end member moments. To find the end member moment at AB, we add up the initial moment and the carryover moment. So anything in this row, in this column, to find the moment at MBA, you add up these, and same thing across all of them. And I've done this here, so you can see. Signs are very important. That's why you can see I've written everything within brackets when adding them up. And then just have a plus sign in between them. And this gives you your end member moments. So these you then substitute in here. And now we are good to draw our bending moment diagram. We have to do this in 2 steps. first we draw this one, then we draw this one, and then we superpose them and we get our final one. So how do we do this one? Here what we're actually looking for is the maximum moment due to the uniformly distributed load and the maximum moment due to the point load. You can see the values, and then this one here, here would be point A. So moment AB from the table we can see is minus 22.913. You draw it on. At point B, we have n member moments BA and MBC. We know they are equal and opposite. Here they are. So at this point, we know the value is 16.665. Now at point C, we have n member moment MCB. And we found this to be 10.417. Now, when we superpose them, what do? You draw this one first, basically, and you point all the moments on here. Then you look at this one and see which moment we have acting. This time they're acting below the axes. So you draw lines up to here, or wherever you feel like drawing them, and write down the value of the moment. So once you have a point here, point here, point here, point here, point here, all the points of moments from the bending moment diagrams above, you can then just draw a line and join them up. This one is curved because we have the uniformly distributed load causing it to be curved. And then this one is straight line due to the point load. And that is it.